Good morning, everyone. We'll just go through a couple of brief meeting logistics. We ask that you please remain on mute throughout. We didn't quite hit the correct setting to get our have everyone on mute as they come on. But we will be recording this meeting, as was just announced by Zoom. And then it will be posted on our Socorro YouTube channel, and we will send out an email with that link. If you have questions, you can put them into the question and answer, into the chat, and we will get to answer those questions at the end of our 3 brief presentations this morning. Emily, if you could go to the next slide, please. Thanks. So as I said, the meeting will be recorded. We'll be very happy to share that recording, and hope that you do have some great questions for our speakers today, because this is a very hot topic, and I think a lot of us are really learning and interested in what's going on with marine carbon dioxide removal around the Southeast. Next slide, please. So just a brief background on the coastal acidification networks. And again, this is I co-hosted with GCAN this morning, which are our partners down to the south in the Gulf of Mexico. The CANs are all virtual networks. Specifically, SOCAN is comprised of an executive team, a science working group, and a stakeholder working group. We are researchers, resource managers, communication specialists, and educators. And broadly, our mission is to work directly with scientists, research managers, data end users, educators, and policymakers to synthesize and communicate the state of ocean acidification and coastal acidification and meet regional community needs. Next slide. So SOCAN is comprised of myself, Janet Reamer, and my co-coordinator, Emily Hall. And we are fiscally housed within Socorro, the Southeast Coastal Ocean Observing Regional Association, and Deborah Hernandez is the executive director of Socorro. Our SOCAN region is Florida, Georgia, South Carolina, and North Carolina, and we overlap with GCAN in the Gulf of Mexico on the west coast of Florida and through the Florida Keys. Recently, SOCAN has been involved in 3 major projects, one of which was assisting with the Intergovernmental Working Group on Ocean Acidification's National Vulnerability Assessment. Then we also partnered with GCAN on a stakeholder feedback project, which we will be releasing the results of that sometime over the summer. And we've also been partnering with folks down at Coastal Carolina University to assess the state of acidification and along Long Bay and Murrells Inlet off of South Carolina. So I'm going to turn it over to Jen Vreeland from GCAN to give you a little introduction on GCAN.
Hi, everyone. My name is Jennifer Vreeland. I am the coordinator for the Gulf of Mexico Coastal Acidification Network. And I'm not going to overlap on what Janet had already mentioned about our work with SOCAN, which we value very highly. We work very closely with SOCAN. The GCAN network covers the Gulf states of Texas, Mississippi, Alabama, Louisiana, and Florida. And we also closely partner and collaborate with colleagues in Mexico and Cuba, which SOCAN is also a part of. And some of the work that we have done this past year in 2022 and 23 was we put together a first international ocean acidification summit that took place in Merida, Mexico. And we partnered with the Hart Research Institute, and we, for the first time, had 29 participants from the US, Mexico, and Cuba to discuss ocean acidification and water quality concerns throughout the Gulf of Mexico. And that was a huge success, and we hope to plan a future meeting We also, again, Janet had touched base on a joint project that SOCAN and GCAN are working on with the, right now, I will focus on the ocean acidification monitoring gap survey project that we're working on, and that's going really well. So yeah, if you are interested in joining one of our networks or both of them, I highly recommend it. It's very interactive and engaging. And we do touch base on not just chemical focuses, but biological, economic. It's very rewarding organization. So I definitely encourage you all to go to the GCAN website that's featured on the slide. And with that, I will pass it on to Janet.
Thanks, Jen.
Yeah.
All right, so today's speakers are Tyler Cyronak from Georgia Southern University. He is a biogeochemist studying how material and chemical elements are cycled through marine and coastal ecosystems. His research focuses on the carbon cycle in such systems as coral reefs, mangroves, seagrass beds, and calcium carbonate sediments. He is interested in the role that these ecosystems play in the global carbon cycle and how they will be affected by climate change. Most of his work involves making seawater chemistry measurements in the field using state-of-the-art technology with a focus on carbon dioxide, methane, total alkalinity, oxygen, and submarine groundwater discharge. And I'll also just mention that this is our second webinar that Tyler has joined us for, because his projects have spanned quite a range of SOCAN interests. Then we will have Dr. Alison Tune will be our second speaker from Running Tide Technologies. She leads the Earth Science and Ecology team, which focuses on the environmental and ecological impact of Running Tide's carbon removal work. She applies her expertise in biogeochemistry to coordinate the biogeoscience research program both internally and with external partners. And then our final speaker will be Dr. Grace Andrews from Project Vesta. She is an aqueous geochemist who has dedicated her career to understanding the Earth's carbon cycle and combating climate change. She works on emerging carbon dioxide removal strategies which address climate change by sequestering carbon dioxide from the Earth's atmosphere. Grace is currently the Vice President and Head of Science for Vesta, a public benefit corporation conducting R&D on an ocean-based CDR strategy called Coastal Enhanced Weathering. Grace received her PhD in Earth and Planetary Sciences from Northwestern University. Following that, she served at the Liverpool, pardon me if I'm pronouncing that right, wrong, Center for Climate Change Mitigation in the UK, and deployed the world's first large-scale pilot projects of terrestrial enhanced weathering, another carbon dioxide removal strategy. So I will now turn it over to Tyler for our first talk.
All right, thank you, Janet. Thanks everyone for being here this late morning. I'm gonna talk to you today about marine carbon dioxide removal and really talk to you about a project that I was a consultant on, and then sort of try and tie in the local coastal ecosystems around here and think about kind of the research that I'm thinking about doing here at Georgia Southern. So I am an academic researcher at Georgia Southern University, and my lab really focuses on the carbon cycle. But next slide. In between positions during this fall of 2022, I was working on a project with the World Ocean Council, which is a sort of cross-sectoral business leadership group that is focused on businesses and enterprises that use the ocean in some way. And the project was funded by ClimateWorks, and it was really to create a business case for marine carbon dioxide removal to try and bring sort of industries that use marine resources together with these nascent startup companies that are trying to do carbon dioxide removal, which I'm going to sort of talk about more right now. So I'm going to give you a bit of an overview of what marine carbon dioxide removal is, and this project specifically, which wasn't fully to look at the entire suite of marine carbon dioxide removal technologies, but really just two in particular, which are ocean alkalinity enhancement and electrochemical processes. Next slide. So I sort of already went over this, the context of the project, why we were going to develop it, and trying to bring together these different sort of enterprises. Next slide. So what really is carbon dioxide removal, and why is there so much interest in it? Really, this stemmed from the IPCC 1.5 degree special report, where the IPCC basically modeled what it was needed to keep warming under an average of 1.5 degrees. And they came to the conclusion that we're going to need to take carbon dioxide out of the atmosphere and store it away in order to maintain our climate goals of being under 1.5. And this really spurred a lot of interest in trying to do that, and trying to take carbon dioxide out of the atmosphere. Next slide. So there's really two sorts of things to think about here, and I really think it's important to describe the difference between these two things, which is carbon removal and carbon capture. So carbon removal is usually CDR, carbon dioxide removal is the acronym, and then CCS is carbon capture and storage. And really, technologically, there might not be any differences between the way you're actually taking the carbon dioxide. It more has to do with where it's coming from. So CCS is generally associated with point source removal. So burning fossil fuels, creating CO2, and then taking that before it reaches the atmosphere and storing it. CDR is really taking carbon dioxide out of the atmosphere that's already there. So it's really thinking about removing legacy emissions that can lead to more climate change in the future. So trying to draw us back down to a place where we want to be able to maintain climate at our climate goals. Next slide. A lot of CDR is based on sort of terrestrial techniques. If you're familiar with anything, it might be direct air capture, which is what this plant is here. And direct air capture is exactly what it sounds like. It's taking carbon dioxide directly out of the atmosphere using some sort of sorbent that bonds to carbon dioxide, and then removing it from the sorbent, usually by heating it, and then storing that carbon dioxide somewhere else. And really, this is great, but it's really energy intensive. And one of the issues is that as far as compared to the oceans, there is a lot less density of carbon dioxide in the atmosphere. Other limitations to some of the other terrestrial CDR methods is resource demands, availability of land, other energy and water use requirements, scalability, and access to storage and sequestration. So next slide. So that really brought us to where marine carbon dioxide removal can shine. And as many of you are probably familiar, about 71% of the Earth is, the surface area of the Earth is ocean. So it really offers a large area to capture carbon dioxide through air-sea gas exchange. And next slide. And also potentially store it. So if we look at the amount of carbon dioxide between the atmosphere and the ocean, in that first box there, that big lighter blue or more vibrant blue circle is representative of the amount of carbon dioxide in the ocean, about 38,000 gigatons compared to about 860 gigatons in the atmosphere. And so really, this is where most of the carbon dioxide exists in what we call the active carbon cycles, where carbon dioxide is moving around relatively quickly compared to sort of the less active carbon cycle, which involves maybe rocks and things like that, where the actual vast majority of carbon on Earth is stored, but it's much, much slower, on the order of tens of thousands to hundreds of thousands to millions of years. Next slide. So the ocean's potential to store carbon dioxide, not only exchange it with the atmosphere, is great because it can be stored as bicarbonate and carbonate ions. And this is really what adding alkalinity is. It's adding these ions that can then capture it. And that allows the ocean to really act more like a sponge and take that carbon and store it as ions in water dissolved, but that aren't allowing it to exchange to the atmosphere anymore. And this can really store carbon for long periods of time, upwards of probably thousands to tens of thousands of years. So the oceans really have 44 times more carbon dioxide than the atmosphere, like we already discussed, making a large natural reservoir. In comparison to land, there's less competition for space in the open ocean, at least, and mCDR targets and accelerates natural CO2 sequestration processes. So we can sort of target things like enhanced weathering, where we're naturally adding out the natural system is adding alkalinity over long periods of time. We can hopefully boost that and do it a little bit faster. And it also offers some potential benefits, such as reducing ocean acidification locally in some areas. Next slide. So what are some of the ways that mCDR is proposed to work? There's a large suite of them. This is from a National Academies of Science, Engineering, and Medicine report that really looked at marine carbon dioxide removal, and you can really divide them into two main categories, ones that use biology and ones that don't. And the ones that use biology tend to grow biomass or enhance phytoplankton growth or marine algae growth of some sort, and then generally try to sink that carbon down into the deeper ocean where it can be stored potentially for long periods of time. The ones that don't use biology are usually relying on the changes in chemistry, like ocean alkalinity enhancement. And so within this report, they divide it up into 6 different types. So artificial downwelling or upwelling, deep sea storage. There were some original thoughts where we could just dump CO2 down into the deep sea, but that really is not something that people are pursuing too much anymore, at least that I know of, because that really would just come back up to the surface ocean over really timescales that we're not looking to store carbon. Electrochemical processes, which we'll talk more about in a second, restoration of ecosystems, seaweed cultivation, and then this ocean alkalinity enhancement, which is adding alkalinity some way to the oceans. And a lot of these overlap in different ways. Even the biological and sort of non-biological processes often can overlap. And I think we'll hear about one of those in one of our later talks. Next slide. So this World Ocean Council project really focused on these 2 processes, electrochemical and ocean alkalinity enhancement. And like I said, they can kind of overlap, and often they do overlap a lot. And they really, depending on how the different processes are done, can really capture CO2 in the oceans, or maybe they're going to capture CO2 and store it in other places like underground reservoirs. So next slide. During the project, oh, whoops, that little one on the bottom wasn't supposed to show up there just yet, but during the project, we worked with multiple startup companies. These are the ones here. And we tried to learn what they were planning to do and maybe what resources they needed. And this, remember, was through the World Ocean Council. So we were trying to join sort of industry and some of these startup companies to be together. And so basically, during that, I kind of looked at all the marine carbon dioxide removal companies that were in existence at the time. And this is probably completely out of date by now, even just a few months later. But overall, there were 26 startup enterprises. And you can see the vast majority were doing some sort of biological biomass removal of carbon dioxide, and then electrochemical and alkalinity were making up the rest. Next slide. So I'm going to move a little quick here because I realize I'm going over a little bit if I want to make it through these slides. But really, ocean alkalinity enhancement, what is that? So it's adding alkalinity to seawater to increase CO2 storage capacity. Basically, you're storing it as ions. When you add dissolved alkalinity, or when you add rocks that dissolve and make alkalinity, you change the chemistry so that the ocean can just take more CO2. It's like a sponge taking more CO2 out of the ocean. Out of the atmosphere and storing it in the oceans. There's really 2 approaches. Enhanced weathering, which is the application of ground rock, either olivine, carbonates, other basalts, to coastal areas. And this is where it really becomes marine carbon dioxide removal, because there's enhanced weathering that's being done on land, especially in places like agricultural fields by spreading basalt and olivine as well. But where it really becomes marine is when you're doing it closer to the ocean, and you can actually enhance the dissolution of these minerals by putting them in places that are a little bit warmer and a little bit more wet, like in coastal regions. And then approach 2 is really the addition of pre-dissolved alkalinity. So adding alkalinity that's been dissolved in a reactor or something like that, and then you're adding it as an aqueous or liquid form. Next slide. Electrochemical processes, these really require energy input, so you need green energy to be put into the system, but they're kind of two broad categories here, which is the direct removal of CO2, and this is really taking carbon dioxide out of seawater, kind of similar to DAX in the atmosphere, but then you have to store it somewhere, and then you put this seawater that has low CO2 back into the ocean, and it equilibrates with the atmosphere, taking more CO2 out of the atmosphere. And then you can also generate alkalinity. So most of the electrochemical approaches basically split seawater into an acid and a base. And you can do interesting things with those two components afterwards. And if you can do something with the acid, like store it or use it to dissolve rocks, then you can add that alkalinity back into the ocean, and you're really doing ocean alkalinity enhancement. Next slide. So there's important things to think about with this, one of which are durability, which is how well the CO2 is going to be stored away. So geological storage is really the kind of best way or most robust storage here, because you're storing it away basically as a rock for really long periods of time. You have to think about the scale potential, so how these different processes can scale. And really how long you expect, so the permanence, how long you can expect the CO2 that you've taken out to stay out of the atmosphere. These are really important components of any marine CDR, any carbon dioxide removal process. Next slide. Another important thing to think about is monitoring, reporting, and verification. And really, this is kind of the most important thing when it comes to introducing these carbon credits back onto a market to sell them for the carbon dioxide removal that is getting stored. Because remember, these are all enterprises that are eventually trying to make money or trying to profit somehow from this. And in order to do that, you sort of have to prove that the carbon dioxide you have captured and stored is really stored and taken out of the atmosphere. And this is really an important thing that is becoming a really kind of hot topic in marine carbon dioxide removal. Next slide. So really, this is going to talk now about more like, well, so I've talked about carbon dioxide removal, the processes that you might be able to store it, some of the things to think about. But really, what is driving this? What's the market that really we can think is going to happen in the future, where you could either sustain the carbon dioxide removal by paying for it somehow or profit from it, something like that. So really, the IPCC forecast calls for up to 10 gigatons per year of CDR by 2050 if we want to stay within our climate goals. And that is a lot of carbon dioxide, and estimated, depending on how you look at the price of that carbon dioxide, that this market could be 500 billion to 1 trillion by the year 2050. So really large growth potential here. Next slide. But where are these carbon credits going to be sold? Really, there's two places now. There's compliance carbon markets, like the one in California, where companies are sort of required to trade carbon credits. And then there's voluntary carbon markets. And these are places where large companies tend to purchase carbon removal for their own sort of portfolios, to either right now invest in the technology or to sort of look forward to removing as carbon credits against their sort of carbon emissions. Next slide. Right now, carbon dioxide removal is really supply constrained from the market, so there just isn't enough out there being sold, and that's because it's really nascent technologies that are really under development, and a lot of these startup companies are really developing the technologies right now as I'm giving this talk, and it's really kind of important to think that we're investing at this stage into these new technologies and really learning how things are going to move forward. Next slide. So if you're interested in this and you're interested in carbon dioxide removal in general, this is a great website. So this is cdr.fyi, and it shows you all of the carbon sales and deliveries that have been made. So not many deliveries to date. That's because a lot of these companies that are investing into carbon removal are really seeing it as investing into new technological developments now. But you can see total sales has really skyrocketed, especially in the past even couple of weeks to month. There was large purchases by Shopify and JP Morgan Chase. So large companies in there buying these carbon sort of removal credits. Next slide. And this was another slide just showing that $400 million in 4 years were invested versus $2 billion in 4 months. So really a lot of money is going into these new technologies. Next slide. So what does the carbon market look like? Like, who are the players in it? So you have people who want to buy carbon credits, carbon removal. There's places that are going to exchange and sell it. And then there's the supply side, the people or companies that are actually doing the removals some way or another, sort of either doing electrochemical or alkalinity or biological ocean techniques, and showing through robust MRV and science that they've removed the carbon. Then they can sell these either at full price or maybe a discounted rate, depending on how long that carbon is going to be stored and how sure we can be that it was taken out of the atmosphere. Next slide. And this really just zooms in on some of the companies and enterprises that are working, and you can see very large companies that are working in this industry. JP Morgan, Airbus, Disney, Microsoft, and a lot of the startup companies are really new and kind of being invested in. You can think of it by these larger companies that are looking to invest in this into the future. Okay, next slide. So my key takeaways from the World Ocean Council project, really as a scientist, so I came in as a scientist with the perspective of an academic and still sort of hold that perspective. But really, I was surprised by just how much is going on now, how much investment is happening. It's really all happening, and we need good science to back up what's going to happen in the future. And so now as scientists, it's really the time to get involved and start thinking about this. This MRV, the measurement, reporting, and verification, is a critical link between the science and marketplace. And in some ways, it's really what carbon removal companies are selling. Like, it's the actual sort of guarantee that they've removed a certain amount of carbon and they're going to store it away for a certain period of time. As far as the science goes, transparency and openness are key to success. You have a lot of different parts of this sort of new, I'll call it an ecosystem, although I don't know how comfortable I feel about that, but this new sort of space where you have startup companies, you have buyers like things like Microsoft, you have scientists who are doing the science behind it. And really, we need to be able to be open and communicate across any boundaries that might be there between these different types of enterprises, because that is really critical to the successful removal of carbon dioxide, which is really what we all want to do, is to reduce climate change. Community buy-in from multiple stakeholders is really important. So like where you're going to do, and you're going to learn more about some of these projects and the specifics in the next two talks, but community buy-in, especially if you're doing things on coasts, is really important, because you can't just go and do these things and not involve the local community. There are, you may have some difficult things to deal with in the future. You can't lose the message of the importance of removing carbon dioxide, and can't really let this become sort of a greenwashing exercise. And then another thing that I think is really important, that anytime there's this much money involved, you're going to have people that are trying to do things maybe not so above the board. And I think it's really important to keep in mind that you can't let that spoil the whole enterprise of removing carbon dioxide, which I think is a very, very important thing we need to do. All right, so next slides, I'm just going to go through real quick. One of the things that's not really thought of as marine carbon dioxide removal, at least not in the technological space, is blue carbon, which is something that's been around for a while, which is really the storage of carbon in marine ecosystems. And they occupy only about 0.5% of the seafloor. We're talking about marshes, mangroves, seagrass, but they contribute to about 50% of organic carbon burial. Next slide. This is just a picture of the three ecosystems showing their carbon burial rates. And you can see salt marshes, mangroves, and seagrasses, all ecosystems that SOCAN and GCAN are interested in, are really critical carbon storage places. So next slide. These ecosystems store a lot of carbon, and we can think about it as the carbon stock. And this is the carbon that nature has already put in the bank. So preserving these ecosystems is really, really critical, because when you start to degrade them, this carbon that's already stored there can be re-released into the atmosphere. Another thing that can be done is enhancing and promoting recovery of these ecosystems in places where they might recover it, although the ability to actually remove a lot of carbon dioxide from the atmosphere by doing that is limited by the space where you can actually promote recovery, which is often combating between human needs like paving over parking lots and things like that, where mangroves used once to be, and you're probably never going to be able to grow mangroves back there. So you're limited to space, really. Next slide. And this is really just where my research, I think, is starting to go. I'm really interested in coastal blue carbon and coastal ecosystems in general. But what about their potential to be coupled with some of these marine carbon dioxide removal techniques, especially alkalinity enhancement? You can think of ways where coastal ecosystems might actually make things better, especially for enhanced weathering, if you're going to spread certain types of material onto things like marshes, where it will hold that material there until it dissolves, and the chemistry might make it easier to dissolve and produce alkalinity. Next slide. So that's really where my research is going to look at potentially, can we do enhanced weathering in marshes, and really look at the safety of that. So making sure that, number one, you're not going to harm the marsh grass and other organisms in there. So doing mesocosm laboratory studies, but also thinking about how you can apply that to a larger field scale deployment. And then also, there are a lot of benefits to the coastal ecosystem itself, such as reducing ocean acidification and also promoting marsh growth by adding extra material in there that'll allow the marsh to keep up with sea level rise a little bit faster. Next slide. So with that, I just want to plug one thing. I am working on this guide to best practices in ocean alkalinity enhancement. If anybody's interested in that, there's the QR code there. I think hopefully these slides will be made available. But this is going to be sort of a guide to how ocean alkalinity enhancement research can move forward from an academic perspective, really. Although there are some enterprises in there as well. But I'm a co-author on one of the chapters here, so I just wanted to plug that. And then next slide, I just want to thank everybody that was involved with the World Ocean Council project and with the rest of my research. So sorry for going over a little bit, but I think I made it through everything, and thanks for your time.
Thanks, Tyler. We will move on to Grace. I'm sorry, no, Allison.
No worries. Hey everyone, I am Allison, and I'll be representing Running Tide today, talking a little bit about the work that we do, and in particular the science side of the company. So next slide, please. So just to introduce myself a little bit, I lead the Earth Science and Ecology group at Running Tide. I came to Running Tide about a year ago, and I did my graduate work at the University of Texas in Austin, thinking about terrestrial weathering, particularly in forest ecosystems, and how that shapes landscapes over time. And I still live in Texas now, so the Gulf Coast is near and dear to me. And now I get to apply that knowledge and expertise in biogeoscience to thinking about ocean ecosystems and ocean forests, really. So next slide, please. But today it is my great privilege to be able to represent the work of Running Tide as a whole. And this company is really made up of a lot of different people with a lot of different skill sets. As you just heard in Tyler's talk, this work requires a lot of different scientific backgrounds, as well as operational and logistical backgrounds. So at Running Tide, we have people who are experts in marine logistics, who are doing really creative manufacturing work, and who are thinking in very detailed lab experiments and macroalgae genetics and things like that. We have 3 major locations where we work out of. Our headquarters are in Portland, Maine. We have a macroalgae research facility in St. Louis. And then we also have operations in Iceland, and there's actually 3 different locations in Iceland, but this map is a little hard to resolve each of those. Okay, next slide, please. But what do we do as a company? So we are first and foremost an ocean health company, and we work on ocean health in 2 key areas. The first is in ecosystem services. So we started as an aquaculture company bringing shellfish to market in Maine, and we continue to do that work, as well as working on places where ecosystems have been altered. For example, thinking of places like wind farms where there's room to restore some of those ecosystems. So that is an awesome part of the company that's really exciting, but will not be the focus of today's talk, since we're talking about the carbon removal side. Next slide, please. And our conceptualization around carbon removal is moving carbon from the fast to slow cycle. This is in line with kind of scientific thinking about how carbon moves in the Earth system. And I'll talk a little bit more about that in the next slide. Next slide, please. And we do this as part of a larger group of organizations. So this work is not possible. As you've seen in Tyler's talk, this work really requires lots of people, lots of organizations. And so we're very proud to work with a lot of different nonprofits, academic groups. Okay, next slide, please. So I mentioned this removing of carbon from the fast carbon cycle to the slow carbon cycle. And I know there are a lot of scientists in the room here, so I won't belabor this point, but basically when we're thinking about fast carbon, we're thinking about carbon that's stored in the biosphere, in the atmosphere, or in the upper ocean reservoirs that's being rapidly cycled. For example, you can think of a leaf that's growing on a tree in the springtime, falls off in the fall, and is degrading over that season. Now, some of that, of course, may go into the soil, and that's part of the natural cycle of fast carbon to slow carbon. But the part that's being rapidly cycled is all within the fast carbon cycle. When we think about slow carbon, we're thinking about geological reservoirs, carbon that's stored within rock formations, the deep ocean that is part of the overturning circulation. And so when we think about movement from the slow carbon to the fast carbon cycle, that would be, of course, fossil fuel burning or other processes that happen in nature, whereas what Running Tide is focused on is taking that fast carbon and moving it into the slow carbon cycle. Next slide, please. And how we do that as part of our technology is creating carbon buoys, which are made from wood residues and alkaline minerals, taking those carbon buoys, seeding them with macroalgae from our nurseries, transporting these buoys to oceans in the location, specific locations in the ocean, which I'll talk a little bit about in a few slides. And then that's where they're then able to float for months, growing macroalgae and sinking into parts of the deep ocean where it can be durably sequestered. And finally, an important part of this is being able to measure the system, being able to monitor what's happening in the surface ocean and throughout our system, really. And so building these verification systems that we need in-house, as well as working with our partners. Okay, next slide, please. So what I just showed you is a very linear process, steps 1 through 5, but in reality, this process is a learning loop. And this is very similar to the scientific method. You could replace these words like prediction and design with hypothesis, or deployment with experiment, verification and monitoring with results. And so next slide, please. In particular, I'm going to talk about these two areas of prediction and design and verification and monitoring, because I think this is where within our process and really within carbon removal technology development as a whole is pretty similar to the work that's being done in the acidification networks, and there's a lot of overlap there. So next slide, please. So our system is working with this open system of carbon in the ocean. There's this really excellent figure from OCB that kind of shows some of those processes happening on a high level. We're thinking about how carbon is being moved from the inorganic cycle in the surface ocean into organic carbon and biomass, and amplifying that natural production of organic carbon and sinking to the deep ocean. Because we work in an open system, this also makes our measurements and the models that we need to use based in the science that exists around these natural systems. So if we go to the next slide, please. And we can make these predictions and understanding of our system by modeling surface transport and sinking using many of these models that already exist in the literature. So for example, you may know about HICOM or ERA5, and using a lot of those same data sets, ocean parcels, so that we can model how our carbon buoys are being transported in the ocean, how we think they'll be transported, and where they'll sink over time, so that we can choose locations where they'll be durably sequestered. Next slide, please. In addition to this prediction part and designing of our carbon buoys and that whole process, we also evaluate the potential environmental and ecological impacts. And so we do a process that's very similar to other kind of external groups where we're cataloging the environmental exposures. This is based on our specific system, so we can think about how we're doing things operationally, how we're designing carbon buoys, and the locations where we're deploying them. We can then evaluate these different exposures by consensus within the academic literature, within nonprofit and governmental groups, as well as what are the governing factors that determine those different impacts. So are they being governed by scale? Are they being governed by the architecture or other considerations? And then we can use this to develop a framework to drive our experimentation and design around these different things. Okay, next slide, please. The other side of this is the verification and monitoring side of the equation. Next slide, please. And this is where our suite of sensor buoys come in. We're using these to make observations and to monitor impact as our carbon buoys and our technology is moving throughout the ocean. So on the left-hand side there, you're seeing left-hand side of the slide, you're seeing two different types of buoys that we use. The top one being a kind of more ocean observation platform where we can observe what's happening to different materials in the surface ocean. The bottom there are trajectory buoys that ping back GPS locations so we can see where our materials are going over time. We're able to see this in real time, both with our camera images as well as data that's coming back from sensors, and apply different tools such as machine vision analysis to rapidly understand what's happening in the to our technology. Next slide, please. In particular, for these ocean observation platforms, we can use these for open ocean experiments. So we've already been able to deploy some sensor suites out into the North Atlantic with our partners in Iceland. And we can see where the buoys are going over time. We can see what's happening to the material within our experimental chambers, our open ocean experimental chambers. And then we can use this to fine tune the parameters in these open source models and integrate that into an applied model platform that can be used for carbon dioxide removal deployments. Next slide, please. In addition to that, we also develop research programs and other experiments that we need to use to evaluate impact. So what you're seeing in these pictures here are some of our preliminary pilot experiments out of Iceland to look at our benthic impact of our carbon removal technology. And we do this for various parts of our system, as well as with additional partners and other locations. And we kind of do this scaling of those research programs and experimental designs from the laboratory scale, where we can do very fast iterations and see any red flags that may be coming up, or test new hypotheses or new materials. We can then move that to the coastal experiments that are a little more involved, a little more realistic, yet a little more affordable than moving to a large location like the open ocean. And then we can finally do these larger open ocean deployments and experiments so that we can understand our system in the open system of the ocean, which is great. Okay, next slide, please. And so just to sum up a little bit of what you've heard so far, we work with the open system carbon cycle. So this is pretty different than some of the other CDR technologies that are looking at a closed system where you're looking at each of these different pieces in a smaller, or at least more closed system environment. And we use this open system to remove carbon and restore ocean health. Research and experimentation is a huge component of what we do, and it's very necessary not only for leading to carbon that's more durably sequestered, but also understanding all of these secondary impacts that are happening as part of the process and contributing to kind of ocean science in general. And the final thing is this is a new and evolving field of study, and as part of this, we're really committed to doing what is necessary to get it right. Transparency is a huge part of this process, and being able to work with collaborators within the research community and within nonprofits is really important. And and is something that we're carrying through as we move forward. So I believe that is my last slide. And thank you all again for having me here. Please feel free to contact me through my email, or we have a contact form at the Running Tide website. And yeah, thank you so much.
Thank you, Allison. I will hand it over to Grace, who will be our last speaker. And I just want to remind folks that if you have questions for any three of our speakers, please go ahead and drop them in the meeting chat. Thanks. Go ahead, Grace.
Thanks, everyone. I can already tell formatting is going to be off, so bear with me. So I'm Grace Andrews. I'm the head of science at a company called Vesta, and we are another startup that is focused on developing and doing R&D into coastal enhanced weathering as a potential marine CDR solution. Next slide. So just a little bit about who we are. I have the privilege of leading a team of about 12 PhD scientists, again, ranging in expertise from marine ecology, microbiology, geomorphology, a whole ton of geochemists, some engineers as well. We are trying to tackle a very interdisciplinary topic, and so it requires a very interdisciplinary team. We have also, a fantastic number of academic partners that we do our work with. I'll highlight a few during my talk, and funding from a number of fantastic groups as well, including NOAA, Grantham, for example. So next slide. Wait, formatting. Okay. So thankfully, Tyler already did a fantastic job sort of giving the overview of how enhanced weathering works. But the upshot here is we are looking at integrating olivine sand into coastal ecosystems, coastal environments. The idea here is that as it gradually dissolves over the course of years to really decades, it generates alkalinity and in turn creates a disequilibrium between the surface ocean, PCO2, and the atmosphere. And so it consumes CO2 in the water, which in turn draws CO2 from the atmosphere back into seawater. And so it's a net removal of CO2. And that the permanence of this strategy is around potentially up to as much as 100,000 years. It's the residence time of DIC in the ocean. And so this has the potential to really remove CO2 and have a meaningful impact on climate change. Next slide. So other reasons that we're excited about it, of course, it's, the primary focus is taking CO2 out of the atmosphere. But I think, our personal take, my take at least, is that these strategies, the ones that are going to likely to be the most successful are the ones that have meaningful, tangible co-benefits. The idea of carbon removal is honestly a little hard for people to often wrap their minds around, especially when you're removing carbon as alkalinity. Nobody even really knows what that is. It's hard to describe. And so having these other co-benefits are a really important part of what I think is what will be successful carbon removal strategies. So with coastal enhanced weathering, the two that really drew me into wanting to do research into it is one, the increase in alkalinity also offsets ocean acidification. So this has the potential to not just mitigate climate change, but also mitigate one of the harmful consequences of climate change. The other one is fundamentally what we're trying to do is add sand to coastlines. That's at the heart of it. It's a sand made of olivine, but it's adding sand to coastlines. And coastlines around the world are eroding primarily or in large parts due to climate change and sea level rise. And so there's a huge amount of work being done to protect coastlines by adding sand back to them. So today in the US, we every year add about 37 million cubic yards of sand to coastlines just for the purposes of coastal protection. Actually, last year was more in the order of 60 million cubic yards. So this is a pretty big societal need. And I'm excited about the potential to be able to add olivine sand to coastlines for this triple benefit of carbon removal, ocean acidification reduction, and coastal protection. Next slide. So at Vesta, we were founded a few years ago, and at that point in the research, coastal enhanced weathering was something that had been explored in modeling studies, in mesocosm, lab-based studies. But what was really clear was that there was a need to do field trials. Or anyone here is a scientist, you'll know you can do about 1 million laboratory experiments and you never really know how something will truly work until you try it in the real world. So that was a primary goal of Vesta when we came together, was to try and actually implement small scale, highly monitored field trials, and then make that data available to the public. So at present, we have done 2 field trials. The first one was in the Herring River tidal marsh in Massachusetts. We started that one about a year ago in a collaboration with National Park Service, Woods Hole, and the USGS. I'd say it was really more of a field experiment. This is very small scale, sort of, 1 meter diameter plots. But the goal here was actually what Tyler was speaking about earlier, this idea that we may be able to integrate enhanced weathering into marsh systems and to blue carbon projects for another co-benefit of contributing and enhancing the alkalinity export from a blue carbon or marsh restoration site, for example. So just like Tyler's really excited about that, we are as well, and have been doing work on that. The other field trial that we started last year was integrating olivine as part of a beach nourishment in New York. So again, super small scale. We've been doing that one with the Cornell Cooperative Extension, Stony Brook University, and of course the local town, the local community. Though I'll share some of the data from that New York field trial to sort of get everyone an idea of how that's been going. And we can take it from there. So next slide. Oh, right. And I'm sorry, getting ahead of myself. The other thing I wanted to highlight before I get into some of the data and the results is some of the other projects that we're developing. So we are currently in permitting for a project in Duck, North Carolina. And a goal with this pilot, different from the other ones, is again, exploring the integration of olivine into different kinds of coastal protection designs. So our 2 field trials, one marsh restoration and the other one beach nourishment. The pilot that we are pursuing in North Carolina is actually placing it as a nearshore berm, so about 1,500 feet offshore. And this one we're spinning up in collaboration with the Army Corps' Field Research Facility, which is also located in Duck, the Coastal Studies Institute, a number of professors from there, and then the University of North Carolina, Wilmington. So that one, again, would be a field trial of just a different kind of coastal protection strategy, but in permitting, but we're planning for a deployment of spring 2024. All right, next slide. So where are we right now? So we, as I said, did our first beach nourishment style field trial about a year ago. The design of this field trial, again, it was integrating about 5,000 cubic yards of olivine sand into a 10,000 cubic yard pilot. 10,000 cubic yard beach nourishment project that was ongoing anyway. So 10,000 cubic yards of dredged material. Over about 1,000 feet of shoreline in the Peconic Bay, so that's Long Island. And so the olivine made up about 5% of the total nourishment volume, so a small component. But what we did, our experimental design here, was we added olivine to about 2/3 of the total project site. So we had about 1/3 that didn't receive any olivine at all. So we monitored just dredged material, olivine plus dredged material, and then we also monitored two sets of control sites on either side that didn't receive any material at all, so just native sediment. And our monitoring program, actually, next slide. before I jump into that, I want to just also take a moment to highlight, some of the work that had to be done before we could actually deploy this material. So stakeholder engagement, of course, is a key component of this. We can't do this kind of work without having community support. So, and making sure that the community is informed. So a lot of work went into getting just information out. So we created a specific website just for this project. We put up flyer boards and notice boxes. We spoke at town halls. We have been issuing a quarterly newsletter on updates on the project. We engaged with the media and got some articles in the local newspapers. We held a press conference. We also started a student scientist program and have had and continue to have local high school students working with us and getting exposure to this kind of to the world of CDR through our project. And it's honestly it's been a fantastic experience. The bottom right picture here is a commemorative plaque. That's actually something that I went out to the site this past weekend over Memorial Day, and in a ceremony with the community, we installed this commemorative plaque at the beach as the location of the first ever field site for a coastal enhanced weathering field trial. And that's the level of excitement and enthusiasm for the project that the local community has. And so it's just been honestly, it's been a tremendous experience. But honestly, probably one of the best in my career. So, all right, next slide. Boy, you cannot see this at all. So this is highlighting our monitoring program and sort of the breadth of things that we are monitoring for at the site. We are monitoring more or less everything under the sun: water, sediments. We're looking at wave dynamics. We've installed a wave buoy out there to collect wave height, things like that. And we have an ecology monitoring program as well, where we're looking at community structure. So abundance, species richness, et cetera. We're doing DNA analyses. We're looking at things like chlorophyll A to see if there's any impact to algae, for example. So kind of anything under the sun, we want to make sure we have a really comprehensive understanding, not just of the carbon removal potential, but of course, any environmental impact, both positive or negative. And our monitoring program is, we're committed to a minimum of 2 years of monitoring, with the potential to extend that further depending on what the data shows and what all stakeholders believe is appropriate. So next slide. Some data I can share with you coming out of the site. So as I said, we have so much data, so I just want to highlight a few sort of interesting data sets. The first one is looking at water quality. Again, this is really important from an environmental perspective. So I'm showing here about 5 months of data from before the project, during the project, deployment, and then after for a number of months of things like chlorophyll A, pH, dissolved oxygen. And we're comparing our data to a number of the USGS monitoring sites also within the Peconic Bay. And basically what we're finding was that there was no discernible, certainly no long-term impacts on any of these. And one of them in pH, I'll point out particularly, I've said one of the things that's exciting about enhanced weathering is the potential to reduce ocean acidification. Just want to highlight because it's a little sometimes counterintuitive, but at these really small scale pilots, the amount of alkalinity that we're generating relative to the volume of water in the Peconic Bay, you're just not going to move the needle on things like pH. So that's anticipated that you won't see an impact on pH. I just want to highlight sort of how that works. Next slide. This is some of the data that has come out of our benthic community surveys. So your benthic organisms, these are your worms, your snails, your clams, anything living in and on the sediment. And we are showing you here 2 sets of pre-deployment data. So May and June, that was before we added olivine, and then August, that was about 2 months after we added olivine. And basically what we're highlighting is that there are seasonal variations in these things, in these metrics, abundance and species richness, but we didn't get any statistically significant difference from the olivine treated site relative to the other sites for either one at the post-deployment time point. So basically that tells us that the benthic communities were covered within that 2-month time period. So that's great. Next slide. We also did an experiment on oysters. So there are no natural oyster beds at our site, but oysters are obviously very important from a commercial perspective. And as many of you will know, are also just generally very good accumulators of pollutants. So if you want to make sure that you're not having an impact on benthic organisms in terms of dissolved pollutants in the water column, oysters are a great metric for that. So what we did was, throughout the project site, we went out and installed oyster bags, again, both in the olivine treated, dredged material, dredged site, and then control sites. And we subsequently went out, we collected them at 2 months. That's what I'm showing you here, also 5 months, and we're doing another collection in a couple of weeks. And we have analyzed them for a suite of trace metals. So here I'm showing you, let's see, lead, copper, cobalt, nickel, chrome. Some of these are important because olivine does contain a trace component of it. So for example, nickel. But ultimately what we found was that there was no statistically significant difference in the oysters that were sitting on basically pure olivine relative to the other sites. So we didn't see any impact from the treatment in that regard. Next slide. And then the last data set I wanted to show you is actually about carbon removal, of course. So, we're interested, as I said, in both environmental impact, but also, of course, documenting whether or not this works to remove carbon from the atmosphere. So as I said, one of the biggest challenges is that olivine, we're specifically at the pilot scale, we're adding a relatively small amount of material into a reservoir the size of, in this case, the Peconic Bay. And the olivine reacts on the timescale of years to decades. So it's a super slow reaction. It's a small amount of material with a super slow reaction into a very large body of water. All that to say, the dilution is significant. And so one of the biggest challenges that we've had is, how do we prove that this is actually removing carbon? As Tyler was talking about, MRV is a really important part of this. You have to be able to demonstrate with in situ empirical data that what you say is happening is actually happening. And so part of our pilot work has been trialing a number of different techniques to try and actually measure the chemical process in situ. So I'm showing you just some data from one of them. This is the deployment of a benthic flux chamber. So basically that's an upside down bucket that sits on the sediment and traps a parcel of seawater within the bucket, right? And so you're capturing the sediment water interface and you leave it out for maybe up to a week at a time. And that allows for the accumulation of the olivine dissolution products in that trapped parcel of water over that week, right? So when you first put it down, there's no difference between your olivine and your control sites. But over the course of a week, that you start to see the pH in the olivine treated benthic flux chamber ticking up relative to the control. And that's what we're showing here, is that when you actually do this, that's what you measure. You see pH ticking upwards. You see the alkalinity in the olivine treated one ticking upwards as well. So all of this is the direct empirical in situ evidence that the olivine dissolution reaction is happening. We're generating that alkalinity. We're seeing that ocean acidification reduction benefit. And this is a pretty central part of our MRV program. Next slide. So I also just want to highlight what we're thinking about in terms of what's next, particularly for this group. So one of the key controls on your olivine dissolution rate, and so in turn your carbon removal rate, is water temperature. That is a primary control. And so for pretty obvious reasons, we believe, it's believed that this coastal enhanced weathering strategy is going to work best in places that have warm water, annual warm water. So in general, Vesta right now is looking for future projects, particularly in South Carolina and the Gulf states. And this map shows you why. These are the places where if this is going to work, it's going to work best in those areas. So we're currently scoping sites in there and hope to be trialing this kind of CDR strategy in those locations in the near future. So, thank you.
Thanks very much, Grace. We have time now to take a few questions from the audience. We'll try to wrap this up at about 12:15. So I'm just going to start at the top from the list of questions that we started receiving. So for Tyler, any environmental impacts to marine ecosystems that you're interested in investigating? That would be in relation to OAE and electrochemical approaches. For example, the impact of temporary high pH and low CO2 levels, i.e. unequilibrated OAE.
Yeah, so I mean, some of the things that are really interesting are what Grace was talking about with the trace metals and potential contamination when they dissolve and the impacts they have on biology. So, I mean, I think it's important, especially if you're going to be deploying it in marshes, to look at how that might affect sort of the keystone species like oysters and some of the marsh grass. As far as actual impacts on the pH and carbonate chemistry, you know, I think that one thing to think about is in coastal ecosystems, there's already really, really strong gradients in pH, alkalinity, DIC that happen on, you know, hourly to daily timescales due to just natural biogeochemical processes. So I think depending on how far you're pushing things out of there, you probably will not have too many impacts from that. Number one, because the minerals take a little while to dissolve, and so you're not going to dissolve them all at once. If you're just dumping, you know, alkalinity in there, you might have shocks to the like super high pH. And really the bigger concern there, I think, is inducing secondary precipitation of like calcium carbonates, because then you sort of reverse the whole purpose of the enterprise or the experiment you're trying to do, because when you precipitate calcium carbonate, you're going to actually make it so CO2 wants to leave the water and go back into the atmosphere. And I think that's probably the bigger concern there. I think the organisms are probably used to pretty strong swings in carbonate chemistry, probably outside the range you would see from the OAE projects.
Great, thank you. The next question we have is to Alison. What types of algae are you working with, and have you investigated or compared multiple species to identify what may be the most efficient and or have the least environmental impacts?
Yeah, this is a great question. So species that we're working with currently are Ovilectrica or sea lettuce and Saccharina latissima or sugar kelp. So we are working with these species because they are both native to the area that we're currently operating out of in the North Atlantic. And that is part of thinking through what species are relevant to reduce environmental impacts to a region. So making sure that we're using species that are native, thinking through which ones are most efficient, that is a huge component of this work. And that is work that's carried out by the macroalgae research side of our organization in St. Louis. So they're an excellent team of scientists and geneticists coming. Quite a few of them come from the agricultural space, so applying some of those same understandings of how vegetation grows and how that can be, made more efficient and that sort of thing. And then I think that goes into the next one as well, a little bit. Focusing on coastal acidification in Latin America. We currently do not work in Latin America, but that's a really interesting thing to consider. And I wonder if some of the other coastal groups are maybe thinking about some of that. And we currently do not have published data on our macroalgae species. However, there is a huge push in the scientific community around nailing down some of those macroalgae growth rates, thinking about that in relation to aquaculture. And then, our role would be applying that to the work that we're doing. So we do have some collaborations around thinking through macroalgae growth rates. As part of our ocean observation platforms that I showed you, that machine vision analysis is not only being used to look at more, the terrestrial biomass or alkaline minerals that are being observed in there, but also the macroalgae growth over time. So a huge part of that macroalgae research is also looking at phenotyping, so the size and shape of blades over time as they're growing and quantifying growth in that way, which is really exciting. Okay, I think that is, hopefully that answers all of those questions. Okay.
All right. Next question is, how would you keep the olivine alkalinity in surface waters where it can help draw down atmospheric CO2?
Yeah. So I guess in terms of keeping olivine in a place where it's going to do its job, it comes down to site selection. You want to make sure that you're picking sites that have an abundant amount of shelf C so that you can stay in a region of the ocean where you do have equilibrium, you do generate equilibrium with the atmosphere. But in general, you can do predictive modeling of that with sediment transport models like Delft3D. The larger answer, though, in terms of how do you keep the alkalinity in the surface ocean is, again, comes down to site selection. So you don't really want to work someplace that's immediately next to a downwelling zone. But in general, the approach that people in this space are taking is to just estimate what amount of your alkalinity may not drive actual equilibration with the atmosphere through things like ROMS modeling, so regional ocean model systems, and to just make a ROM simulation part of your MRV approach. So to actually quantify, if we generate this amount of alkalinity at this project site, are you going to have 70% equilibration, 80%, 90%, and over what time scale? And all of that gets factored into your MRV that's ultimately used to quantify how much carbon you quantify how much carbon you drew down.
Great, thank you, Grace. And then back to you. How sustainable is the acquisition of olivine? How will this change as you continue scaling up these efforts?
Yeah, so currently olivine right now is something that is not in high demand. So it has very few uses. So there is a lot more potential for increasing the amount of olivine production without actually increasing mining footprints, things like that. So right now, we source the largest supplier of olivine in the world, where Vesta is sourcing olivine from for our pilot trials. It's from a mine in Norway, actually, which is surprisingly sustainable. Yes, I know, you're surprised. We are getting olivine from Norway, and we have shipped it to New York for this pilot, but it makes sense. The mining operations in Norway use all renewable energy, and the emissions of shipping olivine from Norway to New York are actually fewer than if you were to truck olivine from a US-based mine. Currently, the only operational US mine is in Washington State. So if you want to do a project in New York, it actually makes more sense to bring it from Norway than it does from Washington, which is, again, counterintuitive, but true.
And how much is needed with dredged material to be effective?
I mean, in theory, you don't need to integrate it with dredged material at all. As long as olivine is in seawater, interacting with seawater and has access to CO2, it's doing its job. There are reasons why you might want to deploy the material in a way that it integrates with either dredged sand or native sand. And that's primarily around just minimizing the concentration of olivine at any one particular point. olivine in many places, although it is found on beaches around the world, is in many places not a native mineral. And so you want to make sure that you're not meaningfully altering the composition of the sediment at any particular site. And that's, again, important for minimizing environmental impact. So that's why for our project in New York, it was about 5% of the total volume of sand that was added to the site, was again to try and keep those numbers low so that it kind of just blends into the background and doesn't fundamentally change your composition.
And we will take one last question, and then if we'll email your questions on to speakers if there are additional ones. Tyler, should private sector NGO companies be required to have a contingency fund to ameliorate any unintended ecological consequences? Sorry, I'm not familiar with that term.
This is a tough question. I think one of the aspects of MRV, and I think a lot of the sort of companies who are working in this space are thinking this, is that part of MRV is understanding the ecological impacts and making sure that there are none. I think there's sort of a do no harm mentality, especially working in some of these ecosystems along the coasts that we really want to preserve for reasons outside of carbon dioxide removal, like shore protection and things like that, and just natural sort of inherent ecosystem preservation. But I think, the whole sort of area or the whole space is working towards figuring out how that's going to be done. And really, I think that's important to do small scale studies first and make sure that there are no ecosystem impacts or negative ecosystem impacts are really, really critical. So scaling up from mesocosm to small field studies before really anybody's deploying this at scale. As to where the money should come if something goes wrong, I don't really know. I'm sure insurance companies will start cropping up somewhere along the way if they haven't already.
Great. Well, I'm going to email additional questions on to our speakers, and hopefully they will be able to get back to you. Or if you don't hear from us, please feel free to email us at socan@socorro.org. Thank you everyone for joining us today, and look out for communications about this webinar to be posted to our website. Thank you again.